Hi, so welcome back, everyone. So I'll be talking about this paper that I wrote last year on the monogamy paradox in empty flat space. Paper was written with Joydeep and Priyadarshi and myself. I'll give a brief review of some other information paradoxes, actually only two, and then I'll talk about the information paradox that we have framed, and then maybe very slight amount of technical details, and then I'll resolve the paradox at the end. So let's start with, the way that information transpires around black holes and in gravity in general is not very well understood. So one paradox is the strong subadditivity paradox. So this is an infalling bunch of matter which forms a horizon at the end. This is forming a black hole. And one finds that these early radiation modes are entangled with the late time radiation modes, but there are also some modes which are on the inside, which results in this violation of strong subadditivity, which is a property of quantum information. And the resolution of this paradox is that there is a firewall, that space-time pinches around the horizon. Another sharper paradox was given by Suvrat in 2019, which did not even require any black hole or any horizon at all, which was just an empty ADS. And there was some resolution with non-factorizability of Hilbert space. We have extended this work to empty flat space. And this paradox has been framed in terms of Bell correlators. And I'll give a brief review of what this particular Bell inequality called CHSH is. So imagine you have 2 qubits, and then there are two observables for each qubit, AI and BJ, and they're both norm 1. And then one can show that one forms this particular correlator. Then classically, this correlator is bounded by 2 from above and below. But quantum mechanically, it's bounded by 2 times root 2. So if the correlator happens to be between 2 and 2 root 2, then we say that the system is quantum mechanically correlated. And if it is less than 2, then we say it is classically correlated. So we are characterizing entanglement between any 2 quantum systems by checking whether this correlator lies between 2 and 2 root 2. If we have a 3-qubit system, then again we can form these 2 CHSH correlators, and one finds that the sum of their square is always less than 8. So you can very easily see that if either of these 2 exceeds 2 root 2, the other has to be less than 2 root 2. So this is a statement of monogamy of entanglement, which means that if A and B are quantum mechanically correlated to one another, then A and C cannot be correlated. They have to be classically correlated. So we are going to put this down in terms of a minimally coupled scalar field theory, which is minimally coupled with gravity in 3+1 dimensions. So phi is our scalar field. What we're going to do is we're going to smear phi in 2 causally unrelated regions. And we're going to show that the modes A and B are entangled with each other, but the modes B and C are also entangled with each other. And that gives a violation in the monogamy. So these are the smearings. It's not very important, the form, but I'll just show that this phi is the quantum field and this is the smearing function. And we can form these annihilation operators, alpha A and alpha B, which are associated with the regions A and B. And one can see that they make these 2 quantum mechanical systems. They commute with one another, and they don't commute with themselves in just the right way to make a harmonic oscillator. There's a projector PS which will be used to make these Pauli matrices for these particular modes, and these are the operators which will use to make these Bell correlators. So you can check that there's a first Pauli matrix, there's a second Pauli matrix, and so forth. And similarly, for the B mode, we have the sum of 2 Pauli matrices, and we have the difference of 2 Pauli matrices. One finds that when you evaluate CAB for this system, for this quantum field theory system, you find that the correlator is this number 2.93, which is slightly less than 2 root 2, meaning it's slightly less than maximal entanglement, which would be somewhere around 2.88. Now let's look at a mode C. This is the interesting bit. So how do we form this mode C? What we do is we take this operator Q, which is localized close to the boundary. This is something that we can do because this projector that we have, which is an approximate projector to the ground state of the system, which we can form because in gravity, it's a well-known fact that in canonical gravity, the canonical Hamiltonian is a term at the boundary. So a projector, which is a spectral function of the Hamiltonian, is also localized near the boundary. So Ci is an operator which is localized close to the boundary, again causally unrelated, and it can in fact mimic the action on the vacuum, the action of Bi. This is kind of the point is not technical, but the way it is proved is a bit technical, but it is possible to do this because there's a theorem called Riesz-Leiter theorem, which guarantees us that we can always form an operator Q of the sort which mimics the action of B on the vacuum. So since B mimics C, since C mimics B, the correlator CAC is almost equal to CAB. And in that case, we actually see that the squares add up to 11.4, which is much, much larger than 8. These are corrections that we get because of the gravitational interaction, and this correction is because of the kind of smearing function that we chose. These are technical points, but the point is that none of these corrections are order 1, meaning that this correlator that we have, which violates monogamy, we would never be able to correct this and bring it under the CHSH bound by applying these corrections. So hence, we have a violation of monogamy by assuming that the Hilbert space of this gravity theory is like a local quantum field. So what is the conclusion is that we found a protocol for order 1 violation of the CHSH monogamy with this approximate boundary projector. The resolution is that, of course, there was something wrong in what we did. The Hilbert space actually cannot factorize like this, and the reason is that Ci contained the projector through this Hamiltonian. And how do we write a projector to a ground state using the Hamiltonian? We say it's something like e to the minus AH, which contains many, many powers of this Hamiltonian. But that's something that we cannot do in low energy effective field theory. So B, in fact, does not commute with C, which is something that we assumed. And it does not even commute with C up to order of gravitational correction, but it actually doesn't commute till order 1. So that's the resolution. Conclusion is that even at low energies, the Hilbert space does not factorize if we have a theory of gravity. And that's it. Questions?
Can you just show this order epsilon term that was coming up?
Yeah.
So this term is coming from. So what is this epsilon?
Right. Yeah. So okay, I'll go back to the smearing. So when we smeared to make these quantum modes, when we smeared the quantum field, we assume that this T has a particular kind of support. The support would be this region and that other region. But there are some requirements on T, meaning that T has to mimic this exponential logarithmic Fourier frequency, and T would also need to be almost flat and would have to die out of a certain region. There is no function which ideally satisfies all of these conditions, but we can make it pretty close. So how close T is to all of these ideals is what the epsilon correction measures. It could never be 0, but it can be done. It can be made pretty close numerically.
Is there a similar statement about when you try to write this boundary operator in terms?
Oh, definitely. So indeed. So even with the boundary operator, in the formation of the boundary operator, we have this approximate projector, and C. So that's why there's an approximation here. So C only approximately mimics B.
And these two things are different. So you
and these two things are independent.
Thanks.
So do we have any other questions? Why was the infrared structure not important?
So great. So all of these excitations that we have, let's see. So yeah, all of the excitations that we have are in the matter sector. So C would never act on this particular. So if you look at this vacuum is smeared over all of these supertranslation modes, supertranslation vacua, but C would never take this state and put it to another supertranslation sector. So yeah, so that's just something that we can bypass by just choosing some kind of smearing, just needs to be normalized. That's all it is.
We have time for one more question, I think. One or two more questions, max.
Hi.
Hi.
So you have used this CHSH inequality. So there are lots of other forms of Bell's inequality violation.
Yes.
So like particularly why you have chosen this CHSH type of observables or something like that, operators?
I don't actually know. We could have taken something else. I don't know. I mean, yeah.
Okay.
This is something that was already worked out in Subad's. This is something that Subad already used in his ADS paper. And this was a follow-up piece of work to that. So I don't know, we could have used something else. This is not a line that I've investigated, no.
Okay.
But we chose Bell inequalities because we did not want to deal with the
that I have understood. I'm just curious that what
entropy. Yeah.
Yeah.
Sorry. Yeah.
What do you
Again, cut off.
what do you actually mean by smearing?
Right. Yeah. Smearing. Right. So smearing means that you take this quantum field, which is a function of position, and you multiply with some function which has some particular kind of support, and then you integrate.
Why does one do it? I mean, I mean, I get that you can always do that, but why do that?
Okay. So. Right. So now I'll have to go into how field theories are defined. So field theory, so these phi's by themselves are actually, these objects are not defined. These objects are always defined under some smearing, because yeah, that's a technical point. But you want to make some quantum system out of a region. You want to, if you want to know about the causal relation between two regions, then you just smear the field in that region.
Thanks.
Okay, so
could I add to that just one thing to the question, to the answer? Yeah, Tunir, perhaps you could have, one more thing is these smeared operators are canonically normalized, and that alpha dagger is 1, right?
Right.
Supposed to being delta function normalized. So that
Right. Okay, yeah.
so when you want the Bell inequalities, you want something that's, that's bounded and satisfies this with 1, then you can make a bounded operator out of it. With the delta
yeah. Field commutation relations always have delta functions on the right-hand side, but we want something which gives us finite answers.
okay. So now we can move on to the next speaker, and let's thank Tunir for this talk.